Hello, I am going to solve problem number 4 of the homework. For problem number 4, we need to find the inductance, which the formula is L equals N, the number of loops, times the magnetic flux divided by the current. And this toroid, which has a height h, and these are the different radii. It has n turns and a current I. The first thing we need to find is the flux. So if we know that flux equals BA, we need to find B first. To find B, we have this picture. If we cut the toroid across, we have that there's going to be a current going out and a current going in right here. And the magnetic field is going to be on the center. So, I'm going to use a different color. So the first thing, I'm just going to create here, that would be path 1. So we have that to find the B, we have Ampere's law right here. So in here, path 1, B equals 0 because there's no current enclosed. If path number 2 is right here, like across with the B field, we have that B is going to be the integral of dl mu naught I enclosed, and we know that our L is going to be 2 pi r. So if we integrate B dl, we're going to have that it's going to be equal to B 2 pi r. And we know that this, due to Ampere's law, is equal to mu naught I enclosed. I enclosed equals the number of loops times I. So we have that B equals mu naught n I divided by 2 pi r. And then for path number 3, which is going to be out here, we have that the B field is also 0 because the net current is going to be 0 because since it's going in here and out here, they cancel out. So this is our total B. Now to find the flux, we know that it's going to be BA. But we need to integrate from radius 1 to radius 2 right here. So we're going to have the d phi b equals b, which is constant, dA. Our dA is going to be h, which is the height of the rectangle right there, multiplied by the change in radius. So that brings us that phi b equals the integral from r2 to r1 of b dA. And this is equal to, well, we have that b equals this up here, mu naught n I divided by 2 pi times h because of the area right here, and the integral from r2 to r1, it's going to be dr divided by r. And then if we integrate this, we get that our answer is going to be mu naught n I h divided by 2 pi multiplied by natural log of r. And when we evaluate for r2 to r1, I'm going to continue over here, we get that our full flux is equal to mu naught n I h natural log of r2 over r1 divided by 2 pi. Since we're trying to find the inductance, we just multiply this. L equals n mu naught n I h L n r2 over r1 divided by 2 pi. And then divide this whole thing by I, so that means just multiply an I right here. These i's cancel out, and these you can square that, so you have that L equals n squared mu naught h natural log of r2 over r1 divided by 2 pi. So that's going to be your inductance for the toroid. And that's your final answer right there.